You've seen them everywhere, right? At barbecues, in hospitals, on construction sites. They're so common, they're basically invisible. But that simple steel tank, it's a total marvel of engineering, and it's holding back forces we almost never stop to think about. So today, we're going to pull back the curtain on the hidden science of the gas cylinder. Because inside that familiar shape, there's a world of extreme pressure, really complex physics, and this constant, silent battle between the gas trying to blast its way out and the container holding it all in. So let's start by looking at those invisible forces at play. Okay, so to really wrap our heads around this, we have to start inside the cylinder. Because everything, and I mean everything, comes down to understanding this immense, invisible force that's just desperate to escape. And the whole story begins with this deceptively simple little equation, the ideal gas law. Think of it as the basic rule book for how gases behave. It just tells us that if you squeeze a gas into a smaller space, a smaller volume, its pressure skyrockets. If you heat it up, same thing, the pressure shoots up. It's the foundational principle for absolutely everything going on in there. But here's the catch. That rule book, it's for a perfect, ideal world. Inside a real cylinder, where the pressures are hundreds of times greater than the air we're breathing right now, gas molecules, well, they stop playing nice. They're packed in so tight they actually start repelling each other, kind of like trying to cram way too many people into an elevator. So to account for all this real-world pushing and shoving, engineers have to use a little correction factor. They call it Z, the compressibility factor, just to get their math right. Now, what's really fascinating is what happens when you're filling one of these things. When you compress a gas that fast, you're not just jacking up the pressure, you're pumping energy into it, and that energy becomes heat. A lot of heat. It's called adiabatic heating, and you've totally felt this yourself. Anytime you've used a bicycle pump and noticed it getting hot, that's it, right there. And engineers have to manage that intense spike in temperature to fill these cylinders safely. So you've got all this incredible pressure pushing outwards. But that is only half the story. The other half is the container itself, which is in a constant, brutal fight, pushing right back. This is that unseen battle of forces. So the first major force the cylinder wall has to beat is called hoop stress. And the name is just perfect. It's the force that's trying to split the cylinder open around its middle, around its hoop. The absolute best way to picture this, imagine an overcooked hot dog or a sausage that just bursts open along its side. Yeah, that's hoop stress in action. And then there's the second force, longitudinal stress. This is the one pulling on the ends of the cylinder, trying to pop those dome-shaped caps right off and just pull the whole thing apart lengthwise. Okay, now this is the secret that basically dictates the entire design of every single gas cylinder on the planet. When you run the numbers, it turns out that hoop stress, that force trying to split it open like a sausage, is always exactly twice as powerful as the longitudinal stress pulling on the ends. This simple 2-to-1 ratio is the golden rule. It's why the walls have to be a specific thickness, and it's why cylinders are built seamlessly, to fight their number one enemy, hoop stress. And knowing that hoop stress is the big bad guy, well, that perfectly explains how engineers choose their weapon for this battle. For just everyday industrial gases, strong and cheap carbon steel gets the job done. For medical oxygen that needs to be carried around, a lighter aluminum alloy is a much better choice. But for the really extreme stuff, like hydrogen fuel cars operating at an insane 700 times atmospheric pressure, for that, you need the best of the best, incredibly light and ridiculously strong carbon fiber composites. Now, you might think all cylinders just hold compressed gas, but it's actually a lot more clever than that. How you store it depends entirely on what you're trying to put inside. So engineers have basically 3 different tricks up their sleeve to pack as much material as possible into a cylinder. The first one is the most obvious. Just compress the gas, like with oxygen. The second is smarter. You pressurize the gas so much it actually turns into a liquid. That's what's happening with the propane in a barbecue tank. And the third method is to go cold, extremely cold. For something like liquid nitrogen, you have to chill it all the way down to minus 196 Celsius until it becomes a liquid. So all of this engineering is designed for perfection. It's this beautiful dance. But what happens when that perfection gets compromised? What happens when that battle between pressure and material starts to go wrong? Now, failure is thankfully super rare, but it can be caused by these slow, sneaky enemies. Rust and corrosion can literally eat away at the steel. Tiny, invisible fatigue cracks can grow over thousands of cycles of filling and emptying. And for some gases, this really bizarre thing called hydrogen embrittlement can happen, where tiny hydrogen atoms actually seep into the metal itself, making strong steel dangerously brittle from the inside out. But the most dramatic failure? It's an event with a name that sounds just as explosive as the event itself. It's called a BLEVE. That stands for a boiling liquid expanding vapor explosion. This is what can happen to a tank of liquefied gas, like propane. If the tank gets ruptured somehow, the liquid inside is suddenly exposed to normal atmospheric pressure. It instantly, violently boils and flashes into this massive cloud of vapor, expanding with catastrophic explosive force. It is the engineer's absolute worst-case scenario. So how do we stop that? How do we live surrounded by these potential bombs safely every single day? Well, the answer is a relentless, rigorous shield of safety engineering. To prevent that worst-case scenario, every cylinder is put through this incredible gauntlet of tests. They're deliberately overpressurized with water to 1.5 times their normal limit. They're scanned with ultrasound, just like a medical checkup, to find any hidden flaws inside the metal. Their welds are literally X-rayed to make sure the bond is perfect. And then, to top it all off, sample cylinders from every batch are taken and intentionally pressurized until they burst, just to prove the design is as strong as they say it is. And all of that testing, all of that work, it leads to this one final, crucial number. A typical cylinder has a safety factor of 2.5. What that really means is that the tank in your backyard or at a hospital is engineered to be more than twice as strong as it could ever possibly need to be in normal use. That huge buffer, that's the ultimate shield of safety. So, the next time you walk past a gas cylinder, maybe you won't just see this invisible, everyday object. Maybe you'll see the invisible forces of thermodynamics, the silent, constant battle of hoop stress, and the incredible engineering shield of safety that makes it all possible. So the next time you see one, what are you going to see? Just a simple tank? Or a masterpiece of engineering hiding in plain sight?